Wednesdays will almost always be the days when I'll be trying to catch up all the loose ends of details that need to be looked at before we. Yeah, that's right. All the details for the homework and for the new lab that we're starting on Friday. So to that end, I'm going to kind of take things in order, though. So what I'm going to do for starters is, I think it was Aaron Danielson, right? You wrote me an email after class on Monday saying there's something wrong with the spectrum plotting function, and I gave you an answer. Did that suffice for you, or? Okay, but now I'm going to fill in the details for those that haven't asked or haven't investigated yet. All the math in the book is good and fine, but when you use the function that I wrote in MATLAB, it has a particular interface that's not necessarily all that obvious. I wrote it the way I wrote it in order to cut down on typing, though. So when you call into this function line spectra, all you have to do is put in DC, let's see, you put in DC plus positive frequencies. And you put in the full x of k coefficient. You don't put in divided by 2 or anything like that. You put it in just as you would read it off from the model. So if we were doing an example like was here in the notes, let's see, I was pressing the wrong button. That's a pain when you use too many different computers. I use like 3 different computers. A Macintosh is one of them and 2 PCs, and the keyboards on all these notebook computers are always, a few of the keys are in a different location. So you got to get used to where are the up and down keys, and they're different on all 3 of them. So from this example right here, if I was to kind of clear some of this stuff out of here, if I want to use the MATLAB function that I wrote on this guy right here, what I would load into it for the frequency vector f, I would put in just the positive frequencies, including DC. So I'd put in 0, 50, and 300, because that's all that's present. And for the x values, I would put in 5, because that's the x0 effectively associated with the DC. And then I would put in 3 times exp of pi over 8 for this term. I don't divide it by 2. And then for the third term, I would put in 6 exp, I have to put a j in there too, exp of j times pi over 2. And that's how I would get the correct plot. If you put in more information than what's required, you're going to get garbage. And I think that's probably what happened to you, Aaron. You probably put in positive and negative frequencies, and the lines just plotted on top of each other is my guess, and you might have not even seen what was going on.
I was dividing the coefficients by 2.
And you were dividing the coefficients by 2, but I thought afterwards you might have not even seen that it was plotting 2 sets of lines.
I didn't have the negatives.
Okay, okay. So if we were to go do that in MATLAB right now, for that particular example, this is the one from the worksheet from last time, but have we used subplots yet? Has anybody used subplots? Okay.
We used them in the fourth one.
Okay. So I put amplitude up above and phase down below. So subplot allows me to address plots as if they were in an array. So the first number that you put in this triple of numbers is how many rows you want to have of subplots, and then the second one is how many columns, and then the third number is which subplot out of the subplots. And the subplots count, if there's a whole array of them, they count from left to right, 1, 2, 3, 4, and then scan across to the next row, 5, 6, 7, 8. So in this case, I only have 2 subplots, so I go 2, 1, says it's a 2 row by 1 column array of subplots. The first one, I'm going to address it by typing that, and then I can go up to my function, which, oops, found too many things from another simulation world. Let's see, what is the name of the function again? Line spectra. That's right, it doesn't return anything. So I'll take this magnitude and clear out all this stuff. So it was 0, 300, and somebody can help me, it'll be faster, 50 and 300. Then the amplitude was what for DC? 5. And then it was for the first frequency at 50 hertz, it had an amplitude of 3 times exp j times pi over, what is it, pi over 3?
Yes.
Then the next one is 6?
Yeah, I think it's 6.
Times exp j times pi over 2. I mean, my brain's not remembering, so like I said, I'd take some help. And there's the plot. So basically you're putting in just the x values as they would be read from the phasor addition formula, although this isn't phasor addition, this is just the line spectra. And then if you wanted to address the second subplot here, then I could repeat what I just did, only I'd change this to phase. And if I want to make it green like I was doing, I'd put G in there. And then that plot is updated. Simple enough. Getting back to the question, why did I do it that way? Because I have a Mathematica function that I was going to show you on Monday, and that one, I didn't write it that way. I wrote it just like the model was developed in the class notes. But this one I wrote first, and this one was trying to make life easier. But sometimes making life easier requires more understanding, and in the end, maybe it doesn't always work because it's not as easy to remember. But that's how you go about using that. Since I'm in MATLAB right now, I'll also point out that I had a question just before class, this df_gen, how do you get access to that? Well, you have to take it off the website. This .p means P code, and P code is binary code, which means it's not understandable except by a machine. Why did the author create P code? To protect the contents is primarily the reason. For whatever reason, they wrote it for the book, and they decided they didn't want you seeing what's inside of it. So you can write an M code file and convert it to a P code file, and you can use and call the function, but you can't see what's inside of it. So by double-clicking on this, this one's already running, or you can right-click on the file, you can say open, and it still gives you the error, but the function is there. So if I was to go access it, like this was an example I did for a student before class, to compare the analysis here when the x value of the vehicle is at 100 meters, and built into this function is that the y value is at 100 meters. So when I hit that without the semicolon, it'll read back the two x values, which is supposed to deliver, and then it delivers the theoretical phase value in degrees. I was just verifying that function is definitely there. You just can't see it. So that's something you need to be able to do if you haven't done it already for the lab that's due on Friday. We'll come back to MATLAB if we need to. Other things on the agenda, I guess we'll go take a quick look at wrapping up this line spectra example, since this is the candidate for the quiz on Friday. It's going to be this type of problem. This was the scribbling we did last time, and the way we left it was we had all of these frequency amplitude pairs written down, and then we just needed to go plot them. So we plotted them by hand. Since that time, I've now posted the solution on the website, done the analysis for the fundamental frequency, and then just put up the computer-generated versions of the plots. These happen to have been drawn with the Mathematica function that I wrote, but the MATLAB one would give the same basic appearance. Now what remains is to finish this one up. And this one just follows in like fashion from example number 1, and you were going to think about this between Monday and now. So does everybody have this one worked out or know what the answers are?
I remember you talking about what you would do given, like on the first example it was 0 and 9, and then on the second example it was 0 and -8. I remember you talking about it, what you would do with that, but I didn't know how to graph it.
Okay. So that's on the first term. What about the second two terms? Are those, is anything too difficult about getting those? Okay. What's the fundamental frequency in this case?
500 hertz.
Okay, 500 hertz. Does everybody agree with that? That's the greatest common divisor into 1,000 and 2,500. Does that follow? I mean, an integer times that greatest common divisor needs to produce the frequencies present in the waveform, and that works in this case, right? Because 1 times or 2 times 500 is 1,000, and 5 times 500 is 2,500. So from a harmonic standpoint, something we're going to be talking about here later in class, the 1,000 hertz sinusoid is what's called the second harmonic relative to the fundamental, and the 2,500 hertz sinusoid is the fifth harmonic. And in this particular signal, what's interesting, and this is kind of something that pops up in the last homework problem, and things we'll be getting into with Fourier series, the fundamental, just like the example or the exercise in the lab, the fundamental is not represented in this signal nor in the spectrum. There's no 500 hertz component present. Just like in the previous example number 1, there's no 40 hertz component present. But that determines the period just the same. And that's something that shows up in your lab actually too. Some of you I've talked to about that in the lab, but obviously I don't talk to everybody because there's 2 of us signing off papers. But just to give another physical interpretation, this is a drawing that I was showing to people during labs on Friday. In this case, because we have a 1,000 hertz and a 2,500 hertz signal, if we were looking at this plot like you do in the lab exercise, you're looking for this period T naught, where you see the waveform repeats. You know, you have a squiggly line, and you can notice just from your eyeballing it that it repeats every so many seconds. Call that T naught. That's the smallest period, or the smallest value where the waveform repeats. So in the case of F naught being 100 or 500 hertz here, how many periods of the 1,000 hertz are in T naught? 2, right? So if we were looking at this as an interval of time for the 1,000 hertz signal, we'd see 2 complete cycles, and I'm just denoting that as if we're looking at a time record as a vector of data in MATLAB, and I'm saying there's 2 complete cycles contained in T naught. And then for this one, approximately, I didn't draw it as good as I could probably. There's 5 periods in there, right? And that's the whole greatest common divisor business. We're trying to get this congruence thing going where we get an integer number of periods of one and a different integer number of periods of the other one such that we can have things match up. So it takes 2 of one and 5 of the other in this case. But there is no signal that has a period of T naught in this case that's represented, but there's a space for it. And if you're a musician type person, you'd say everything has to be harmonically related to make beautiful music. That's not true in all countries of the world, though I think some countries of the world, harmonic relationships, they don't care about. Maybe some of you listen to that music, I don't know. It sounds a lot different than what we're used to, though. Okay, so in terms of working this out then, getting back to this -8 business, that is in polar form, that is 8 e to the j plus and minus pi. Because after all, from Euler's identity, that would be 8 times the cosine of plus or minus pi plus j times the sine of plus or minus pi, right, in terms of a polar to rectangular. And this is obviously 0, and that's -1. So in polar form, -8 is just 8 at an angle of either plus pi or minus pi. And so that tells us that in the magnitude plot, we just plot the magnitude, which is 8, and on the phase plot, we plot either plus pi or minus pi. That's all there really is to it. But
so on the magnitude, you would just graph it at 8,
and
then on the angle, you would draw it below and above the.
You would draw it one way or the other, and on this example, since I already put it up there, it would be as shown there, either at pi or it could be at minus pi. So this thing in here just says it could be either way. You can do it either way you want to. I think in my plotting functions, I chose to plot it at plus pi, but it's equivalent.
So, but you can't draw it as like both?
No, it's one or the other. It's because of the modulo 2 pi nature of complex or angles of complex numbers. I could draw it, I could say it was 3 pi too, right? That would also be fair, but that's not reduced mod 2 pi. Any odd multiple of pi would be the proper angle, because if we're thinking of the complex plane, just put a unit circle on here. If we were thinking of vectors in the complex plane, we're just talking about something that lies at this angle over here. So I can say that that's at pi, or I can say that that's at minus pi, or I could say we go 1.5 times around, or in either direction. Is that reasonable?
Yeah, but then on the 1,000, at the point 1,000 on the angle one, how come it's positive? Wouldn't it be negative?
1,000?
Yeah.
Let's see. I probably entered something in wrong. Yeah, I've got something that's wrong in here. What did I do wrong?
The positive 1,000 should be on that.
Oh, I see what's happening. Yeah, never mind. Good question. You're bothered because this isn't like that, right?
The opposite of that.
Well, again, because of the way the function was written, and this one was in Mathematica, I didn't keep the symmetry. So actually, I should write a patch up in the software to catch that. But it still works either case, right? It doesn't really matter. It's just how pretty is the picture is what it really comes down to. And you're bringing up a good point. One of the properties that will I think, talk about in this introduction to Fourier series is that the magnitude plot is always even. In this plot down here, the phase spectral line plot is always odd. So to make it appear odd, we really should have the sticks going in opposite directions at the positive and negative frequencies, but where things break down is at pi, because pi and minus pi are equivalent to each other. So it's kind of like that beauty of the odd or even symmetry kind of gets messed up if you...
So in this situation it works because it's pi, but if it was like pi over 2, it wouldn't work?
Exactly. Does everybody understand her question? Pi is special, so it can serve both roles. And when you're new to this, anything that breaks consistency is something that's kind of shattering to your trying to get your understanding going. And I can see where in the beginning you're thrown off by that. But it turns out it's the same thing. So I probably should fix my function. If you're writing software, what would you do? You would say if the angle is pi, make sure that the angle on the opposite side at the negative frequency gets plotted with a sign change on it. So I'd have to put in some if then else kind of a statement in my software to do that. So now I'm motivated to go spend some time on that amongst a bunch of other things that I should be working on. So, okay, that was a good question though. Because if you're bothered by it, somebody else is bothered by it or is soon to be bothered by it. It's good that you're bothered by it now. When you're bothered by something late at night and you're tired, you probably convince yourself that you don't know what you're doing anymore, and then you just close the book and go to bed, and you still don't have your problem solved. Okay, I've put up on the website a hints page for set number 3. So we're going to be referring to that as we go through the material here in Chapter 3 some more. Before we get to Fourier series, though, we have one other thing to go to, and that is we did beat notes last time. I have my audio system hooked up. Actually, yeah, good comment. Good that I'm thinking of that. What you're going to be playing with in the pre-lab, and when you get into in the lab for sure, is you're going to be running this GUI function called beatcon. And I don't think beatcon fits all that well on my little screen. I might be able to make it work. But this is what you're going to be playing with in the experiment. You're going to be using your headphones, and you're going to be doing things with beat notes. So this is a GUI that they wrote to do all that stuff. Bring the Advil? That doesn't sound too bad, right? Well, you're going to be demoing it, and I'm going to be walking around listening to it over and over again. So but what I do is exactly what you said. I do not plug it in my ear. I hold it at a safe distance to make sure it doesn't cause damage to my hearing. You actually, you're going to have another lab that's going to be on synthesizing bell tones, and that one's quite a bit of fun too, where you're actually looking at how to create a certain type of timbre by changing some parameters in a waveform called frequency modulation with an envelope decay to synthesize a bell tone sound. In the end, it's not going to sound like a real bell, but it's going to be a simple approximation to some type of a bell tone sound. Okay, what we saw in looking at this, along the way of looking at the beat notes, was that we had an occasion to bounce into the trig identity that says cosine times cosine is cosine of the sum. Oops, let's see, got to get this thing back again. Little flakiness that I've occasionally run into here. Let's see. Cosine of the sum and cosine of the difference. So in this particular example where we had cosines at F1 and F2, we got a sum frequency and a difference frequency. So as the example unrolled last time, we had an F naught and a F sub delta is what we were dealing with. Actually, it was F sub delta over 2. So that one frequency was, the frequencies are separated by F delta when you get done with them, centered on F naught. Well, that actually provides an opening for something very fundamental to communications theory, and it's a particular type of modulation known as amplitude modulation, or AM. And I think we had this discussion before, but maybe I'm thinking of my communications lab that I teach after that. When you think of AM radio, what pops into your head? Doesn't sound good, but what do you think of? Man, I know I didn't ask you guys this. Boring? Sports? And what else? Talk radio, right? That's about all it's used for right now. But it does have a nice characteristic in that AM radio signals are at a much lower frequency than the FM broadcast frequencies are. So when the ionosphere shifts at night, we can get skip going off the ionosphere, which means a radio station in New York City can be picked up here in Colorado Springs. FM radio is a much shorter wavelength, and it just penetrates through the ionosphere. It does not bounce off of it. So AM radio, you can listen to stations a long ways away at night, and the way that actually happens is that there's only so many channels on the AM broadcast band, and there's lots of stations around the country. So the premier stations that were there first have rights to broadcast with full power late at night, and the lesser stations have to reduce their power, because otherwise everywhere in the country everybody would hear every AM radio station on that frequency assignment all superimposed, and it would be nonsense. So that's how come certain stations in Chicago and New York are heard, because they were the original holders of the license rights, and they get to keep their power at full strength at night, whereas the lesser stations, like in the podunk communities all over the country, they have to shut down to a very tiny power so they don't interfere. Has anybody ever done that? Listen to stations long ways away? Okay.
XM.
That's satellite. That's different. I have that in my car, and that's actually much better, right? If you have satellite radio. How many people have either Sirius or XM since they merged? Okay, you're the only one that knows that. If you're traveling by yourself and you don't have anybody to talk to except yelling to yourself or listening to your CDs, satellite radio is actually pretty good, I think, because it never goes away except when you go under a bridge, because you can't get the satellite signal, and there's a buffer in your radio, just like a buffer on a internet radio station, so the buffer times out. So if you're stuck in traffic and you have to go under a bridge, then it will time out, and then it comes back as soon as you can view the sky again. But there's live DJs that are always talking to you and kind of keeping it interesting, not just simply playing music tracks back to back without talking, depending upon which one you want to listen, what channel you want to listen to. Then there's HD, and there's actually HD radio for AM and FM both, believe it or not, and they both aim to try to improve the fidelity. That's an overlay standard that exists over the existing broadcast band. We could look that up on the internet and talk about how it works, but let's not get too sidetracked. Let's stay on AM radio. So AM radio, how do you form a transmit signal? Well, you form it by having what's called the carrier signal. So this would be the carrier. Like, where is the station that somebody mentioned that you listen to sports on? 850 kilohertz. So that's 850 times 10 to the third hertz is where that FC, or carrier frequency, is located. Definitely above our hearing range, right? We can't hear things up there. Bats don't hear things that high either. I do have some bat recordings I'll play for you. Maybe I'll do those here even today, because I've worked at the Cheyenne Mountain Zoo on a bat echolocation project with some seniors quite a few years ago. At any rate, cosine 2 pi FCT, the 850 kilohertz, and then we put out in front of it, through a multiplication operation, an amplitude. So this relates to the signal strength. How much power do you want to radiate into space off the antenna? That's what that AC is for. And then in square brackets, 1 plus beta times m of t. Beta and m of t constitute what's called the message. Beta is just a parameter called the modulation index. And typically, if we were to let m of t, if we were to basically scale m of t so it never exceeds 1, or actually say has magnitude strictly less than 1, then beta would take on values between 0 and 1, and that would control what's called the modulation index. And for an AM radio station, you have to keep the modulation index below 1, or also known as 100% modulation, and that has to do with the way the receiver can easily recover the information from the modulated carrier. So when I say modulated carrier, what I mean is the carrier over here getting multiplied times that 1 plus beta m of t. That operation is known as modulation. Just moments ago, we saw multiplying a cosine times a cosine produce a sum and difference frequency, and that is the basic behavior of AM radio. We're going to modulate the carrier by multiplying by a message signal. In the case of a single sinusoid message, it's just a tone, and it produces two tones then, one that sits above the carrier by the message frequency and one that sits below the carrier. So in the time domain, when you carry out this operation in equation 316, this is what the signal looks like. The high-frequency carrier, which would be at 850 kilohertz, not 100 hertz like it is here, would just be a very short duration or short period signal. And if we were looking at it in MATLAB, what would we be seeing, do you think? If I plotted this with 850 kilohertz in a MATLAB plot, what would we see? It'd just be solid blue shaded in there, because there would be so many cycles in there. It'd just all be hazed in with a bluish color. We'd have to zoom way in on it to see the individual cycles. In this case, the message signal is only at 5 hertz. In a typical AM broadcast medium, they can broadcast with frequencies in the message that go up to about 5 kilohertz. And therein lies the problem. That's why AM doesn't sound very good, because they're only allowed to broadcast spectrally message frequencies up to 5 kilohertz, whereas high-fidelity audio we think of as going up to 20 kilohertz, with our hearing, tapering off around 16 kilohertz in that neighborhood, depending upon our age and abuse to our ears. So that doesn't sound very high-fidelity-ish listening to AM. But that's the same quality that you have in a cell phone, too, because that's basically called speech grade quality, and that's what you have in a cell phone as well. So when we see the modulation index here, beta is equal to 1/2, we can see that the modulation is just causing this envelope fluctuation. So the carrier amplitude, rather than being steady, when we multiply it times 1 plus beta times m of t, it's fluctuating up and down like this. And as long as we keep it less than 100%, we'll never cross 0 here. If we were to drive it right up to 100%, we'd be coming down. something like that. But as long as we keep it below 100%, there's no touching zero right in there. And that means we can use a simple detector known as an envelope detector. When you study electronics later on, you're going to find that if you were to process this waveform through a diode circuit, a resistor, and then a capacitor, the diode rectifies the signal, so it throws away all the negative half of the waveform, anything at negative voltage values. And then combined with the capacitor is going to stay charged up in between these individual cycles so that what will come out, let's see if I can pull the right pen up here. So what approximately will come out will be that, which is the original message signal in this case, the original sinusoidal message signal. Now it's on a DC bias at that point, but that can be removed with a level shifting circuit in electronics or a coupling capacitor. So that's why AM radio was so popular in the early days of radio. The receiver is very, very easy. Everyone could own a transistor radio. Before that, they could own a vacuum tube-based radio. I mean, whatever. You could go to Radio Shack today and you can buy a crystal receiver. Has anybody ever played with one of those? Just a coil of wire and a little, in this circuit basically, and a little earpiece. No batteries required. Just plug the ground wire into a ground in your house, like a heat duct or something, and then just have this long wire strung out on the floor, and a simple tuning element would be out in here, an inductor and another capacitor. So this would be a tunable capacitor, and you'd put an antenna on this, and you can build an AM receiver with just those parts right there. No one's ever done that before? You haven't lived yet. You need to go to Radio Shack and buy one of those experimenter kits for probably less than $10.
How far can an AM radio signal transmit? Like, what's the maximum without it bouncing off the atmosphere?
It's going to basically be line of sight then, and that's what, because FM, when it radiates off the tower, we get it line of sight. Or think of, I'm looking at Cheyenne Mountain down there. There's an antenna farm down there is what I call it. You ever noticed all the sticks on the top? Those are all the broadcast stations for Colorado Springs. So it's line of sight, basically. So we have curvature of the Earth. FM shoots out all across the hemisphere above the antenna, like your wireless LAN antenna would. But when it goes up high, it just dissipates. It goes through the ionosphere. It doesn't reflect. And AM would be bounded the same way if it didn't curve and then also bounce. That's why you study electromagnetics. And, those are other options you go into in electrical engineering, other aspects. You can see circuits. It's showing up fields and waves is in here too. So if we go plot that AM signal, first we decompose it using the trig identity. So when we actually do the math over on this, let's see, this equation here, the cosine gets multiplied times 1 in AC, so there's a pure cosine. So this is known as the pure carrier signal. And then the cosine also goes times, times the 1 times the beta cosine 2 pi f delta of t. And now we know that that produces a sum and a difference, because you just think cosine times cosine, we get cosine sum, cosine difference. So we're going to get a component at FC minus delta and FC plus delta. So knowing now that we have these three components present, what is our line spectra going to look like based on what we've done so far? Each cosine term contributes how many spectral lines? 2, one at the positive frequency and one at the negative. So how many should we have total? 6. Does that make sense? Each one gives us 2. So there they are. we have the 100 hertz, in this case, which was the carrier frequency. For KRDO, that would be replaced by 850 kilohertz. And then the single tone message at 5 hertz, which would be not really audible, we'd raise it up to some higher frequencies or just have a message signal on there that would fill the spectrum in more rather than just spectral lines. But at any rate, in this case, we have something at 105 and 95, and then the same matching set at the negative frequencies. So when we have to demodulate this signal, effectively what we're doing is we're going to take, effectively what we do is we take that whole cluster of signals and we move them back down here, and then we can recover the message. And that's how we'd hear the message. We'd hear the 5 hertz sinusoid, and then this is the DC, which we would block or get rid of with the level shifter. And that's what that envelope detector effectively does. That's what this little bit of electronics does. Don't need digital signal processing. You can do it with DSP that we learned about in this class, but you can do it with just 3 elements like that, some amplifiers and things. So you probably are thinking, why do we go to school to learn all this stuff when some things we can do so easily? Well, it's just the way it is, but you already said AM radio is no fun, so we moved on to bigger and better things. We made our life more complicated. Right? I mean, you can say that's true as well. The military, AM radios just, it would be utilized for certain things, but it doesn't have certain amounts of robustness for jamming and so on. But guess what? AM modulation is used in a very important application still to this day, and that's the aircraft bands that are around 110, 115 megahertz is where AM signals are located. Just above the FM broadcast band is where planes communicate with the tower through an analog voice means. So Colorado Springs, for example, reuses, on our cable network, we reuse all of those frequencies to receive signals on the cable band. And so we have, as a requirement, you've probably seen the cable Comcast trucks driving around with their little antennas on them. Why do you suppose they have antennas on their cable truck? To look cool, well, yeah, that's part of it. What happens is if you don't have your cable system properly shielded and screwed into everything tightly, your cable will leak RF energy, and that energy can be picked up by that antenna on that cable truck, so they use that to see if you're leaking signal, because the Federal Communications Commission says, yes, you can have a closed-circuit network and rebroadcast signals on these cable frequencies, but we have other users, namely aircraft bands and other public service bands that are licensed for free airspace use, and if your cable leaks and causes interference, that's a violation. And as a person that does fly occasionally, you wouldn't want to know that somebody's whacked out wiring in their house was causing some radiation out of their house, and an airplane flies over and gets jammed and can't talk to the tower or something. That'd not be too cool, I don't think, right? The spectrum helps tell us what's going on, though. So they would have a receiver that would basically be a spectrum analyzer, and they'd be able to see where that leakage is occurring, and then they can turn that antenna and directionalize and find out which house it's coming from and go in and deal with it. I think in the olden days you might have gotten fined, but I don't think they do. I don't think they fine people. They just come in and they say you need to have better wiring. It's happened at our house where they've said your cables weren't, the shields weren't good enough, and they come in and take the old ones off and they give you new ones and tighten the fittings down so that they're tighter. Has anybody ever had that happen? Okay. Maybe it's only because I've jerry-rigged things in my house that I've caused problems. And I didn't bring a spectrum analyzer home to see if I was causing a problem. So now we can go look at a homework problem. you've got the homework problem, which, let's see, I didn't open that one up here today. Come on. You've got this problem right here, which is kind of the opposite of what I just worked in the notes. I'm giving you the spectrum. So this looks like the AM spectrum we were just looking at. And I'm saying now from the spectrum, go backwards and find out what AC, beta, and FC are. So really the hint that I put out for this problem says you really work A and B pretty much together. So you go from the spectrum and you go backwards and you determine, what every parameter is, AC, beta, FC, and M of t. You'll identify M of t from that. So that's what I say in the hints page over here. And this is available on the website right now. So if you've been studying that problem, or if you glanced at it and said, I'm confused, this is to let you know this is where it keys off of what we just went through, and the hints page here is to help you work it backwards. So in the notes, it's done in the forward direction. You just have to work it backwards. I'm giving you the spectrum, and then you have to unravel what the signal is, whereas what we just did in the notes was we had the signal and then developed the spectrum. Sound doable? Or you can take a stab at it and see what will happen. Let's see. Did I close something? Yeah, I did. How did I do that? For whatever reason, that disappeared. Okay, the other part of the notes we've already talked about in following this section is the greatest common divisor when you have a collection of sinusoids. So we've already gone through this. I think everybody's good on this. This is one of the easier calculations to do in concepts. Does anybody have any questions? It's true, though, that you don't always have a greatest common divisor. You can't always find that frequency. And last week, I got into this business of saying, oh, we have a square wave, which we're going to be looking at here with Fourier series, and it would nominally have just odd harmonics in its representation. It would require all odd harmonics, but here I've just done a model that I'm just going to approximate a square wave using the first, third, and the fifth. And I know from analysis that I make the fundamental have an amplitude of 1 and 1/3 and 1/5. I know that that makes a square wave. 1/7, 1/9, and 11th, and so on are added to make it approximate the true square wave. So if I put that up in MATLAB using the strips function, I can see that, yes, it's periodic by eyeballing it. It doesn't look like an ideal square wave. It has squiggles in it, but it still is approximating that just using the first, third, and the fifth harmonic. But then I went ahead and tweaked the frequencies of the third and the fifth harmonics slightly. Instead of being 90,000 and 250,000, I tweaked them by one integer, and then plotted this out, and it doesn't look so good anymore. Now, because the computer is going to do even a rational approximation, eventually this waveform will repeat, but it's going to take a very, very long time. In other scenarios, though, the waveforms, the sinusoids that would make up the composite waveform might actually not be standing at a constant frequency. They might be drifting relative to one another. Kind of like if you had two clock oscillators in a microprocessor or computer system, they wouldn't stay in sync with one another unless you phase lock them. So they would drift around, and so the waveform that would be produced if you sum those together would never be periodic, because there would always be some drifting going on. And this just shows the spectrums look essentially identical at this distance, but if we were to zoom way, way in with a spectrum analyzer, we'd see that they're not exactly equal. Okay, the next topic, and this is the most math-intensive topic so far this semester, is Fourier series. We're not going to do a deep drill down on it because it's not possible for this class to get that in depth without kind of getting you really frustrated and irritated. You can come back and visit this some more in circuits and systems later, some more Fourier analysis. But for starters, what Fourier discovered back in 1807 when he wrote his thesis was that any periodic signal can be represented as a sum of harmonically related sinusoids. And the approach that our book takes is to express that as a sum of complex sinusoids, a doubly infinite series of complex sinusoids. So having a sum that runs from minus to plus infinity onto itself is one source of math that can sound intense. You can say, I need to have an infinite number of harmonics with both positive and negative complex sinusoids to represent a periodic signal. That's absolutely true. The fact is, though, that you don't need the coefficients a sub k probably are going to eventually get very, very tiny and not be all that significant. So a square wave clock, for example, or any clock signal that you'd have in a digital circuit would be periodic, and these coefficients a sub k with the complex sinusoids are used to then synthesize mathematically that waveform. So there's a synthesis formula which tells you how to synthesize in terms of harmonics, and then there is an analysis equation which tells you how to get the coefficients from one period of the waveform. So this is the other side of the Fourier model. It's saying if we want to analyze a periodic signal and break it down into its Fourier components to know how strong is the fundamental, how strong is the second, third, fourth, fifth harmonics, and so on, we have to go through this integration. And this integration gets to be kind of tedious because the functions that you can plug in there for x of t and with a complex sinusoid are just tedious to integrate. The math just gets bothersome. And I'm going to show you some examples. The one coefficient that you're going to be able to do, and will probably be the subject of another quiz at some point, is at least solve for the DC component, the A0 coefficient. That one's pretty trivial, but it gives you a flavor for what's going on, and you'll do some modeling in MATLAB as well. If we have, and then a special case is if x of t is real, then we have the property that the coefficients that sit at the positive and negative indices in that doubly infinite sum are conjugates of each other, which means that from Euler's identity, we can put those two complex sinusoids together and always form a real cosine. So we have the same idea that we had with the phasor addition formula. We have x sub k's, which would come about from our original models that we were using, where we have an AK as the magnitude and a phi k as the phase, and then that would form our signal up as a DC term, the A0, plus real sinusoids at all the harmonic frequencies. This T naught here is the period. 1 over T naught is F naught, which is the fundamental frequency. Right now you should just be saying operationally it looks okay. I'm not really excited about doing the math, but the idea makes sense to me. That's what you should be saying. Does it make sense? A good example is when you pluck a guitar string. That's one good example from physics. That string vibrates at more than just one frequency. Have you looked at that in physics or anywhere in maybe high school physics? Remember how that works? There's different modes, waves that can exist as the string is plucked. It will vibrate at its fundamental, and then there'll be a node or nodes and antinodes. So then we'll have two waves on it. You'll have three, and depending upon the nature of the vibrating whatever, it could be playing a brass instrument or any wind instrument. You have the same idea. You have some column of air or a string or something that supports multiple modes, and those different modes of vibration then are the harmonics. And that's what the Fourier model is saying. You have these different harmonics present. Mechanical systems have the same behavior too. The example I think of there is maybe your suspension system on your car. When you go over a pothole or something, it actually sets into motion some vibrations, and those vibrations have fundamentals and second and third and fourth and fifth harmonics associated with them. So there's a long, lengthy derivation of getting at this analysis formula, which I'm going to go through. But because there's a homework problem number 4, I want to just kind of give you something that is very doable before we go back and prove all this math. And that example is the first example. So we have the analysis and synthesis equations. Right now, we're just going to focus on the synthesis idea and how to go about getting the analysis by sort of a backdoor approach. For homework problem number 4, we can use an alternate approach to analyze rather than that integral. So if we go about getting the spectrum of a Fourier series, it's just like what we went through in the beginning of the chapter. We have the frequency-amplitude pairs all over again. But before we actually do that, let me just look at this example and see how we can get a Fourier series representation for even a very simple signal without having to use that actual analysis equation. If we have a cosine squared 2 pi 1500t, what is that going to be composed of if we break it down? It should have some Fourier representation because we know that's a periodic signal. It's just not a cosine. Now it's a cosine squared. So if we square it out, what do we get when we square out the cosine? Well, in this case, I squared it out after I applied Euler's identity, but you can always just use a trig identity, right? If you had cosine of theta squared, that gets you cosine of what? 1 plus cosine of 2 theta. Why do I know that so quickly, even though I've memorized it in the past? Why should you be able to know it, though? We were talking just a few moments ago about cosine of alpha times cosine of beta, and that, remember, was 1/2 the cosine of alpha plus beta times cosine of alpha minus beta. So cosine squared is a special case of that, right? Where I'm just taking cosine of theta times cosine of theta, so I'm going to get sum and difference. So I get 2 theta, and then I get cosine of difference, which is cosine of 0, which is 1. So if you don't remember that trig identity, you can kind of reprove it using the one that we just went through. So if we look at this simple form right here, how could we look at that in terms of the Fourier decomposition? We just apply Euler's identity to it and say that we've got just a pure DC component, and then this term right here is just an e to the j, 2 times something. And then we have a plus e to the minus j 2 times something. And that's exactly what's going on in here. When I applied the square, after I applied Euler's first, I got a DC term, and then I got a 2x frequency term and a minus 2x frequency term. So when I get done with this, I'd say, oh, looking back at the general Fourier synthesis formula, I'm looking to see how I can represent x of t in terms of some amplitudes and some complex sinusoids. That's exactly what I have right here. When I do that decomposition, I can see when I'm done with this thing, I've got x of t now being composed of a 1/2, so that must be the coefficient that goes with k is equal to 0, and the k is equal to 2 term, if I consider f naught to be the original frequency of 1500, 3000 would be the second harmonic. So the coefficient that goes with k is equal to plus 2, because it's sitting with this plus e to the j term, what should that coefficient be, according to our synthesis formula up here? It's got to just be this guy sitting right out in front of it, right? It just sort of pops off at the page at you, and you say, oh, that's the coefficient that goes with the k is equal to 2 term. So that's the 1/4. And then at the minus second harmonic, this is k is equal to 2 minus 2, and this is k is equal to plus 2, which I've written down there already. It's also 1/4. So the Fourier series for this simple signal, if we treat the period or the fundamental frequencies being 1500 hertz, is synthesizable using a DC term that has amplitude 1/2, and then coefficients at the plus and minus second harmonic are 1/4 and 1/4. And then all of the rest of the Fourier coefficients are 0. They're not needed. Thinking back to the signals we were looking at in the example sheet, remember not all the harmonics were present when we did the greatest common divisor. Maybe it was 40 hertz, but we didn't have anything until we got to 440. That's what Fourier's theorems, Fourier series properties say. We have an underlying fundamental, we have placeholders, but the coefficients can be 0 by and large for some types of signals. For square waves, that's not true. We have all the odd harmonics, and other types of waveforms we have even and odd harmonics, but for simple signals, it's just a few harmonics. So I'm watching the clock, and I can see what's going to happen. So for problem number 4, I'm giving you a signal that has 3 cosines in it, and I'm saying by direct expansion into complex exponentials, find the Fourier series coefficients. So on the hints page over here, I gave a long hint, and I gave this very long hint, which I'm not going to read because I didn't know how things were going to go today. So this is some background and backup material to kind of explain through it, and I'll let you read through that. But if you just look at what's going on here in the problem set, the first thing you need to do is take this term right here and multiply it out. So that's a cosine times a cosine. That's going to give you cosine of a sum and cosine of difference then, right? So when you do that, then you'll be able to write x of t in terms of three distinct cosine terms. And then you can identify what the Fourier coefficients are directly from that. And then you'll also be able to identify which harmonics are present, because you'll be able to look at the individual frequencies. You'll have an F1, F2, and an F3, and you know how to find the fundamental frequency, right? The greatest common divisor. And then you'll be able to see which harmonic numbers those frequencies correspond to, which integers times the fundamental give you F1, F2, and F3. So, for example, in finding the Fourier coefficients, there'd be a pair of Fourier coefficients from that guy, right? It's at 5 hertz, But what coefficients would it have? It would have, from Euler's identity, that would expand out into 25 times e to the plus j, that frequency, plus e to the minus j, that frequency, over 2. So what are the Fourier coefficients at the plus and minus 5 hertz harmonic is 25 over 2, right? I don't know what harmonic number that is yet, because I don't know whether that's k is equal to 1 or k is equal to 21. I won't know that until I can assess what all 3 frequencies are, and that won't come until I work that term, expand that term out. So this is like a baby Fourier series problem in that it's just done by inspection. You just have to expand it out into the 3 cosine terms, and then you can go each term one at a time to figure out what its coefficients are. So for starters, how many Fourier coefficients will be active in this signal? Anybody want to venture a guess?
6.
Okay, one person says 6. Anybody else want to take a guess? Either vote for 6, or say I'm not sure, or, well, say why it's not 6, maybe. Anybody else agree? Okay, I saw 1 thumbs up. How about a show of hands? How many people think it's 6? Okay. Why don't you think it's 6?
Isn't there another one at 0?
A DC term?
Yeah.
For a DC term to appear, how could a DC term appear out of this? Or if a DC term could appear if that product there gave rise to a DC term, and how can that give rise to a DC term? Because when you take the product of 2 cosines, you get the sum frequency and the difference frequency. So to get a DC term, we have to get a term that's at 0 frequency, and that means the difference frequency would have to be 0. Do 20 and 100 have a difference frequency of 0? No. So what are the frequencies that you would get from that product there? 80 and 120. Does everybody agree with that? So we pretty much have the problem halfway's worked now. We have a 5 hertz, we have an 80 hertz, and we have 120. And each one of those cosine waves gives rise to 2 spectral lines, plus and minus frequency, and each of those frequencies, then the plus and the minus, have a Fourier coefficient. There's one corresponding to the negative frequency and one to the positive. And there's 3 of them. So the original assessment of 6, now do you agree, the more people agree that was correct, or not so? There's no DC in this case. We'll spend more time on this next week, for sure, on the Fourier stuff. But what else did I want to do? There's one other thing I want to look at before we get out of here, and this is to help you with the lab. The lab is going to look at some simple things with the tones and things, but then it's going to go off and do something entirely new and different, and it's beyond all this Fourier analysis, which is pretty detailed math. But I want to take you through it and try to at least expose you to it here roughly and show you on the next assignment what you're going to have to do. I'm also going to give you a demo, probably not this Friday, but next Friday, of this idea called the frequency tripler, and how it uses Fourier analysis to synthesize, without using any phase lock loops, it'll synthesize a signal at 3 times the frequency of the input using known properties of Fourier series. And I'll show that to you on the spectrum analyzer, on the network analyzer. But the next topic that's kind of thrown into the end of this chapter, which has kind of a big airplay, or earplay I should say, pun intended, in the lab, is not this keyboard stuff, although that's interesting. Spectrogram you're going to get introduced to, but there's something in here called chirp signals, and you're going to see those at the end of the lab on Friday. And you're going to be going away from the lab saying, I'm puzzled. The very last part of the lab has you create a chirp signal, and a chirp signal is a linear chirp, is just a frequency that goes linearly increases in frequency and maybe goes back down again. It will chirp up or chirp down. It's kind of like a police siren, just a linear frequency chirp. So the analysis for that is based in this section of the notes. So if you want to read about it, you can look in the book, of course, but you can look starting on page 342, and we'll be getting into this. But one of the fundamental things is you're going to write a little program that does the chirp, which is implementing this equation right here. But you're going to have to say design a chirp. You'll have one part of the lab that will say build a chirp signal that will go, say, from 100 hertz to 1,000 hertz in 1 second. That'll be a requirement. I mean, not this exact example, but something similar to this. So you'll want to come back and look at this example and see how it is that you're going to come up with the coefficients that you have to have. You have to be able to determine mu and F naught from the requirements. And the requirements come down to 2 equations and 2 unknowns. Everybody can handle that, right? 2 equations with 2 unknowns. You basically say you want to start, in this case, at 0 seconds at 100 hertz, and you want to end at 1 second at 1,000 hertz. And then from those 2 equations and 2 unknowns, you can solve for F naught and then back around and solve for mu, so that you can take those and plug them into your synthesis equation here that you're going to program in MATLAB, so you can generate the chirp signal to listen to it, and then also look at it in the time domain as a linearly increasing frequency, or look at it in the spectrogram domain as something that over time increases in frequency from, in this case, it was designed to go from 100 hertz up to 1,000 hertz in exactly 1 second. And you'll be listening to these going into your brain too. These can be annoying if they're too loud too. But then there's a little something at the end, which is the lead-in to the next chapter that will be intriguing. I'm not going to tell you what it is right now. You're going to discover this on Friday, though. Remember, this lab is an all-in-one lab, so. But I will help fill in that mystery, because we'll get into the next chapter as well, and then that will start explaining what aliasing is and what's going on.